Hello everyone, my name is Ernest Chikwado Daniel. Welcome to PCH 332, Pharmaceutical Analysis 1. Today we'll be talking about titrimetric analysis. Now, titrimetric analysis is also known as volumetric analysis. Titrimetric analysis or volumetric analysis involves a Nning method in which volume is a signal. Now, volume here is a signal. Unlike gravimetric analysis where we react zinc chloride in the solid form with say silver nitrate, probably in the liquid form, to form zinc nitrate and silver chloride. To balance this, we have zinc chloride, then we have 2 and 2 and 2. Now, normally in gravimetric analysis, we measure the mass of the zinc chloride. We're interested in their masses. We measure their mass and we measure the mass of the precipitate to know the analyte and the known solution. But in volumetric analysis, we don't use mass, or titrimetric analysis, we don't use mass. The volume is the signal. The volume is the signal. It involves a stoichiometric reaction of the titrans and the analyte. Now remember that stoichiometric reaction means whatever you are reacting, you must ensure that they are balanced. Because if you are reacting your titrans and your analytes, they must be in stoichiometric form. For example, saying HCl plus Na2CO3. We know HCl is an acid. We know Na2CO3 is a base. Reacting it, some can say NaCl plus H2O plus CO2. Now, this is perfect. Is this perfect stoichiometrically? No, because we have 2 sodium here. Now, normally, if you look at this reaction like this, it is not stoichiometrically complete. It is not complete because the sodium is a 2 in the reactant side. Sodium is 1 in the product side. So using this formula, you won't get your final answer. You have to balance it. Balancing it now make us put this as 2. Putting this as 2 will ensure here as 2. Now it shows that everything is complete. So that's why in a titrimetric analysis, the analytes and the titrans are reacting stoichiometrically in equal volume, or must be balanced. The equation must be balanced. That's what stoichiometrically means. It must be balanced. The equation must be balanced. Now let's talk about what titrans and analytes is. A solution whose concentration is known and is usually in the burette is a titrans. So far you know the concentration of what you are about to use, the solution you're about to use, and the solution is always in the burette. We know what the burette is. That solution is called a titrans. It has a known concentration and is usually in a burette. A titrans has a known concentration. The concentration is known and is usually in a burette. Why an analyte is a solution whose concentration is not known. You don't know this concentration, and is titrated against the titrans. The titrant is coming against it. Usually in a conical flask. It is usually in a conical flask, though some people might use beaker, which is informal, but the formal method is using a conical flask. So also an analyte can also be called a titrand. Some texts call it titrand. You will not feel confused. Some texts call it titrand. They can say titrat, titrand. When you see titrand, it also means titrans. They're talking about that's also talking about analytes. So I will give a diagrammatic representation of titrimetric analysis, where we have the titrans in the burette. This is your burette. The titrans is always in the burette, and remember I said the titrans is of known concentration. Probably say it is of 10 molar, and the analyte or the titrand, which is also always in the what? Conical flask. Or this is of what? Unknown concentration. We don't know this concentration. It's after our after the titration, whatever volume we get here, we will use it using this formula CAVA CBVB to get the concentration of the analyte. That is why they said titrimetric is a what? Volume is used as the signal because everything we are doing involves volume and volume. So now, I believe we've understand of what titrimetric analysis is all about. We've understand it is a volume signal. It involves stoichiometric reaction of the titrans and the analytes. The titrans is always of known concentration and is usually in the burette. The analyte is of unknown, or we don't know the concentration, and is always in the what? Conical flask or beaker, and it is titrated against the titrans. Also, you can also call it the titrand. Now, we want to talk about the classification of titrimetric analysis. How are they classified? Now, titrimetric analysis is classified into 4 various classes. We have the first class, which is the acid-base titration. From the word acid-base titration, it simply tells you that we're talking about an acid and a base. It involves an acid or a base titrant reacting with an analyte that is a base or an acid. What this simply means is that if you have your titrant as an acid, definitely your analyte should be a base. Then if you have your titrant as a base, your analyte should be an acid. You don't have, for example, let me use that the same HCl plus NaOH. Now, this will be your titrant, and this will be your what? Analyte. Or this can be your titrant, and this can be your analyte. Depends on what you are looking for. If you know the concentration of NaOH, and finding the concentration of HCl, your NaOH will be your titrant. That's known concentration. The HCl you're looking for will be your analyte. But if you know the concentration of HCl and you're looking for the concentration of NaOH, your HCl will become the titrant and your NaOH will become the analyte. You can't do it for acid and acid or base and base. You can't say your titrant will be an acid and your analyte will be an acid. It doesn't go that way. They won't react. You can't say your base, your titrant is a base, your analyte is a base. It can't go that way. They won't react. Why it goes that way is because when they react, they'll form a salt and water, which is giving us HCl plus NaOH. That's giving you NaCl, which is the salt, and water. But if we say HCl plus sulfuric acid, definitely we don't know what we're getting because this is an acid. It contains proton. What is reacting? We don't know what to react. If we say ammonia plus NaOH, definitely nothing is reacting because we have a base and we also have a deprotonated hydrogen. Deprotonated hydrogen, which shows that it's an acid, which shows is a base. These two can react because it won't react to give anything. So definitely in an acid-base titration, it involves an acid or a base, that is a titrant, reacting with an analyte that is a base or an acid. So acid base or base acid. I gave you an example here, HCl and NaOH. Now, complexometric titration. Complexometric titration involves a metal and a ligand complexation reaction. The metal should always have an ion. Could be calcium and EDTA. We'll talk about that in the equation down. Also, we'll talk about redox titration. Now, redox titration, this involves the titrants as an oxidizing or reducing agent and the analyte a reducing or an oxidizing agent. Same goes the way like I talked about acid-base titration. In redox titration, redox reaction occurs between an oxidizing agent and a reducing agent. So if your titrant is an oxidizing agent, your analyte should be a reducing agent. If your titrant is an oxidizing agent, your analyte should be a reducing agent, vice versa. I give you an example, KMNO4 and ferrous 2 titration. Now, precipitation titration. This is one in which the analyte and titrant react to form a precipitate. Okay, that example is ZnCl2 plus AgNO3. Now, in this reaction, they react to form a precipitate. One will be soluble in the aqueous one will be soluble in the aqueous form, and the other will be soluble, forming a precipitate. Now we measure the volume of that precipitate and we get our analyte. That's it. Now the equation of all this I've talked about is given here. This is an acid-base reaction between an acid and a base where we form NaCl, which is the salt, and water. A complexometric titration between calcium 2+ and EDTA, forming a metal ligand complex. This is a metal ligand complex. This is a metal and this is a ligand. When they react, forms a metal ligand complex. Then this is a redox titration between KMnO4. KMnO4 here is +7. Coming here, it is reduced to what? +2. You see that this is an oxidizing agent which is reduced. It could be the analyte or the titrant. If it is the titrant, means we know the concentration of KMnO4. But if it's the analyte, we don't know the concentration of KMnO4. To react with ion 2. Now look at ion 2 here as oxidation state of +2. Going over here, it comes as an oxidation state of +2 or +3. What does it tell us? That this is a reducing agent that has been what? Oxidized. It's an oxidizing agent that has been reduced. So one might be the analyte, one might be the titrant. So if this is the titrant, means we know the concentration of this, and we are reacting with it, and with the analyte, if we don't know the concentration, they'll react together to cause this one to be reduced and cause this one to be what? Oxidized. Then this is a precipitation titration between zinc chloride and AgNO3. When they react, this will form a white precipitate. And this will dissolve. We measure the volume of this precipitate and we get our analyte.